Today we will be discussing diagonalization of matrices. We begin with the following example. So we are given this 3 by 3 matrix, and we want to find eigenvalues and eigenvectors of A. And we are given the characteristic polynomial of this matrix. So determinant of A minus lambda I is equal to minus lambda cubed plus 2 lambda squared minus lambda. And it is straightforward to compute the characteristic polynomial of a matrix, and I just don't want to spend time in this lecture verifying that this matrix does have this characteristic polynomial. When we find eigenvalues and eigenvectors of a matrix, the first step is solving the characteristic equation. So here we equate the characteristic polynomial to 0. And now we need to find the roots of this polynomial. And the easiest way of doing this is by factoring. So here we have a factor of minus lambda times lambda squared minus 2 lambda plus 1. And so here this is a perfect square. So we get minus lambda times lambda minus 1 squared is equal to 0. And so eigenvalues are roots of characteristic polynomial. Once we find eigenvalues, the next step will be to determine the eigenspaces, or rather we would like to find bases of eigenspaces. And we do it separately for each eigenvalue. So we're going to find the basis of an eigenspace corresponding to lambda equals 0 and the basis of an eigenspace corresponding to lambda equals 1. Now we begin with lambda equals 0. So in this case, so lambda equals 0 eigenspace. So here eigenspace for lambda equals 0. So this is just the kernel of the corresponding operator, or kernel of the matrix, or the null space of a matrix. To find this null space, we need to reduce this matrix. So the first step will be, so we say new row 1 is minus 1/2 of row 1, and then the matrix will be 1, 1, negative 3, 12, 9, negative 24, 3, 2, negative 5. And so then we say that new row 2 is row 2 minus 12 row 1, and new row 3 is row 3 minus 3 row 1. So this gives us the new matrix, so 1, 1, negative 3. So here we get 0, 9 minus 12, that's negative 3, negative 24 plus 36. So this is going to be positive 12. And so here we get 0, 2 minus 3 is negative 1, and minus 5 minus negative 9, so this is 9 minus 5, that's going to be 4. Now we see that the last two rows are proportional, and so what we see is that the row echelon form of this matrix is the following. So 1, 1, negative 3, 0, 1, negative 4. So here, if we multiply this row by minus 1, we get this, and the last row will be eliminated because they are proportional, so we'll have zeros. And we actually are guaranteed that if we are treating an eigenvalue of a matrix, then A minus lambda I will have a 0 row in its row echelon form. And so now to find the reduced row echelon form, so the last step is row 1 nu is row 1 minus row 2. And we get the reduced row echelon form will be 1, 0, 1, 0, 1, negative 4, 0, 0, 0. So here we see that the rank of this matrix is equal to 2, and this means that dimension of the null space of this matrix is equal to 1, because this is a 3 by 3 matrix, and we know that rank plus nullity is equal to the number of columns. And now, since we have a one-dimensional eigenspace here, so we can write x1, x2, x3, and so here, so x3 is a free variable, x2 is going to be 4t, and x1 is going to be minus t. So our conclusion is that lambda equals 0 eigenspace has dimension equal to 1 and a basis that consists of a single eigenvector, which is minus 1, 4, 1. So this vector is an eigenvector for this matrix with eigenvalue lambda equals 0. So this means that it's killed by this matrix. And any other eigenvector corresponding to this eigenvalue is a non-zero scalar multiple of this one. Next, we're going to deal with the lambda equals 1 eigenspace. So here we need to consider a matrix A minus 1 times I. So this matrix is going to be, so we subtract 1 from the diagonal elements. So minus 3, minus 2, 6, 12, 8, negative 24, and 3, 2, negative 6. And here we see that this matrix has proportional rows. So if we multiply the first row by negative 4, then we're going to get the second row. And if we multiply the first row by minus 1, we are going to get the last row. So this tells us that the rank of this matrix is equal to 1. And then the reduced row echelon form is obtained by dividing the first row by negative 3. So we get the matrix 1, 2/3, and negative 2. And the rest will be 0. So because the rank of this matrix is equal to 1, so this tells us that the dimension of the kernel of this matrix is equal to 2 by rank nullity formula. And so we also see this from the reduced row echelon form. So here, when we describe the null space of this matrix, we need to use 2 free parameters. So let us do this. So here, when we write down our solution space, so we will use parameter s for x2, parameter t for x3, and so then x1 is equal to minus 2/3 s plus 2t. And so then we can write this as s over 3 times the vector minus 2, 3, 0 plus t times the vector 2, 0, 1. And we conclude that the basis of lambda equals 1 eigenspace is the following set of vectors. So we have minus 2, 3, 0, and 2, 0, 1. Next, let us put these sets of vectors together and form a set of 3 vectors. So we take minus 1, 4, 1. Then we take minus 2, 3, 0. And we take 2, 0, 1. It is possible to check that these 3 vectors are linearly independent. and thus they form a basis of R3. And so this basis consists of eigenvectors. So the first is a lambda equals 0 eigenvector, and the last two are lambda equals 1 eigenvectors. Now let us think of this matrix as a linear operator. So here we have a linear operator from R3 to R3, and T applied to a vector V. So this is given by multiplication by this matrix. So it's A times V. Let us ask the following question. What is the matrix of operator T in basis B? To answer this question, we recall our mantra. To form a matrix of a linear transformation, compute images of basis vectors and place their coordinates as columns to form a matrix. Now let us give names to our basis vectors. So we'll call them V1, V2, and V3. If we want to find the matrix of this operator in basis B, so then when we are talking about basis vectors here, we are talking about vectors of these bases. So this means that we need to find images of V1, V2, and V3. But we know how to do this, because T of V1, since V1 is a lambda equals 0 eigenvector, so this is just a 0 vector. Then T of V2, well, V2 is a lambda equals 1 eigenvector, so this means that this is equal to simply to V2. So this is lambda times V2. And T of V3 is equal to V3. Now let us construct matrix of T in basis B. And we will call this matrix TB. So in comparison, this matrix A is the matrix of this operator relative to the standard basis. So we're going to call A is TE. To construct the matrix TB, we take images of basis vectors and place them as columns. So the image of the first basis vector is a 0 vector. So we put 0, 0, 0. Now, what should we put as the image of the second basis vector? The image of the second basis vector is itself. Now, we need to put its coordinates as columns. But now, when we talk about these coordinates, so these coordinates will be also relative to the basis we are working with. So this means that we need to put coordinates of V2 relative to the basis V2. But what is V2? V2 is equal to 0 times V1 plus 1 times V2 plus 0 times V3. And so this tells us that the coordinates of V2 relative to the basis B is 0, 1, 0. And likewise, so the image of the third basis vector is V3. But the coordinates of V3 relative to the basis B is going to be 0, 0, 1. So what is the meaning of the matrix T in basis B? If we apply operator T to an arbitrary vector and want to know the coordinates of the result relative to the basis B, so this will be equal to the matrix of this operator in basis B times the B coordinates of vector V. This is completely analogous to this formula, only this formula is given in the standard basis. So this formula can be rewritten as T of V relative to the basis E is equal to the matrix operator T in basis E, which is the matrix A, times the standard coordinates of a vector V. And since our standard coordinates are our default coordinates, so when we write a vector without any subscripts, so then we mean the standard coordinates of a vector V. So these are two different ways to write the same formula. So here we see a trade-off. So now we have chosen a new basis, which is more complicated than the standard basis. But the gain is that the matrix of our operator in this new basis is much simpler than the original matrix. And this is something that we're going to exploit to our advantage. Now that we have the matrix of this linear operator in the standard basis and in the non-standard basis, let us ask the question, can we find a formula that relates the matrix of T in the standard basis and the matrix of T in the non-standard basis? To find this formula, we recall what is the change of basis matrix. So if we have a non-standard basis, then we obtain the change of basis matrix C, B to E by placing the vectors of the non-standard basis as columns. So we'll get the change of basis matrix is -1, 4, 1 as the first column, -2, 3, 0 as the second column, and 2, 0, 1 as the last column. Now, what does the change of basis matrix do to us? So if we take change of basis matrix B to E and multiply by the B coordinates of any vector, then the result will be the E coordinates of the same vector. So this means that this change of basis matrix recalculates B coordinates of a vector into standard coordinates of the same vector. Let us take an arbitrary vector V and let us look at the standard coordinates of T of V. So by this formula, so this is equal to TE times VE. And the matrix of this operator in the standard basis is the matrix A. So this is equal to A times V, right? So we identify a vector V with its standard coordinates. Now let us calculate the same thing, so the standard coordinates of T of V, in a different way. So we're going to perform the change of basis. So we're going to write down that this is the change of basis matrix times the non-standard coordinates of T of V. So this will be T of V in basis B. So we take the image of our vector V and calculate it in basis B, and then change the coordinates from non-standard to standard. But here we have a formula that tells us what is the B coordinates of T of V in terms of matrix TB. So what we get is that we have change of basis matrix times TB, so the matrix of T relative to the basis B, times the non-standard coordinates of a vector V. And this change of basis formula has a counterpart. So here, this formula says how do we go from basis B to the standard basis. But we also have a formula that tells us how to go from standard basis to non-standard basis. And so here we use the change of basis matrix CE to B times the standard coordinates of a vector V. And the change of basis matrix from E to B is the inverse of the change of basis matrix from B to E. So if we apply this formula, then we get the following result. So we have change of basis matrix from B to E times the matrix of T in basis B times, here we put change of basis matrix from E to B times the standard coordinates of a vector v. Since the left-hand sides in these two equalities are the same, then we can equate. So TE times VE is equal to change of basis matrix from B to E times the matrix of T in basis B times the change of basis matrix from E to B times the vector VE. And here, so this vector VE is arbitrary. This tells us that we can equate these two matrices. So that TE, so the matrix of T with respect to the standard basis, is equal to the product of three matrices. So the change of basis from B to E times TB times the change of basis from E to B. Indeed, so if we have this equality for arbitrary vectors VE, so if we take VE to be vector 1, 0, 0, then here this will be equal to the first column of this matrix. And then we conclude that the first column of this matrix is equal to the first column of this product. If we take VE to be the vector 0, 1, 0, then we will obtain that the second column of this matrix is equal to the second column of this matrix, and so on. And so if this equality holds for all vectors VE, so then these two matrices must be equal. Now, this equality actually makes perfect sense. So the matrix TE tells us how to apply operator T in the standard basis. But now this gives us a slightly more complicated procedure. If we start with any vector v in standard basis, multiplying by this change of basis matrix, we'll obtain the b coordinates of this vector. Then applying tb, we're going to obtain b coordinates of t of v. And finally, recalculating from b to e, we obtain the standard coordinates of t of v. So thus, the result of application of the right-hand side is the same as the result of application of the left-hand side. Now, this formula is called the change of basis formula for a linear operator. If we want to simplify our notations, so now let us call this change of basis matrix simply as C, and this matrix, let's call it D, because this is a diagonal matrix, and so diagonal matrices will usually denote by letter D. Then this formula can be written as, so on the left we have the matrix of T in standard basis, which is A. And here we have that A is equal to C times D, and this matrix is the inverse of C. So we get that matrix A is C times diagonal matrix times C inverse. And this is called the diagonalization formula. Even though this change of basis formula looks more complicated, I prefer it to the diagonalization formula, because personally I can never remember what do we have in diagonalization formula first, C or C inverse. Another way of writing the diagonalization formula, so if we multiply this formula by C inverse on the left and by C on the right, then we will get that C inverse AC is equal to D. So this formula can be read in two different ways. So we can express A in terms of the diagonal matrix D, or we can express this diagonal matrix D in terms of matrix A and the change of basis matrix C. This diagonalization procedure not just gives us some nice algebraic formula, but it's a powerful computational tool. In the upcoming lectures, we will see powerful applications of the diagonalization formula. Now, let us recall, why did this matrix came out to be diagonal? So this happened because this special basis that we have chosen was a basis of eigenvectors. And in this diagonal matrix, so here, so we have eigenvalues of our operator T on the diagonal. And this operator had eigenvalues 0 and 1. And 0 eigenspace was one-dimensional, and lambda equals 1 eigenspace was two-dimensional. And so because of this, we have two ones on the diagonal. And in the change of basis matrix CB to E, we have the standard coordinates of eigenvectors as columns. Let us do one more exercise on matrix diagonalization. Exercise: diagonalize the following matrix. A is -2, -5, 1, 4. We begin by computing characteristic polynomial. So here it's determinant of A minus lambda I. So here we know that for 2 by 2 matrices, the characteristic polynomial is lambda squared minus trace of A times lambda plus determinant of A. And so here this becomes lambda squared minus, so the trace is the sum of the diagonal entries. So this is minus 2 lambda, and determinant here is going to be, so minus 8 minus -5. So this is going to be minus 3. So we get lambda squared minus 2 lambda minus 3. And then the characteristic equation is lambda squared minus 2 lambda minus 3 is equal to 0. And the left-hand side factors as lambda plus 1 times lambda minus 3 is equal to 0. And the eigenvalues are the roots of the characteristic polynomial. So what we get is we have two eigenvalues. So lambda 1 is equal to -1, and lambda 2 is equal to 3. Next, we find the eigenvectors, and we treat our eigenvalues separately. So we want to find the eigenspace for lambda equals -1. So we consider the matrix A minus lambda I. So this will be A plus identity matrix. So this matrix will be, so we add 1 to diagonal entries, -1, -5, and 1, 5. And we are guaranteed to have a 0 row in row echelon form. And indeed, so here we see that these two rows are proportional, and the reduced row echelon form will be the matrix 1, 5, 0, 0. And so the rank of this matrix is equal to 1. So rank of A plus I is equal to 1. And this tells us that the dimension of the kernel of A plus I is also equal to 1, which is 2 minus 1. Which tells us that there is a single eigenvector, or the basis of this eigenspace consists of a single eigenvector. So here, if we write down the general solution for the null space, so we're going to use T as the value of the second variable, and then we get minus 5t as the value for the first, and then the basis of lambda equals -1 eigenspace is the following vector. So we'll have vector -5, 1. Now we repeat this procedure for lambda equals 3 eigenspace. So here we take the matrix A minus 3i. So we subtract 3 from the diagonal. So we get minus 5, 1, 1. And again, the reduced row echelon form will have a 0 row. So this is the reduced row echelon form. The general solution for the null space will be minus t, and so the basis of lambda equals 3 eigenspace is given by a single vector minus 1, 1. Now we put everything together. So we write down what's the basis of R2 consisting of eigenvectors of t. So here we put these two eigenvectors together. So we have minus 5, 1, and we have minus 1, 1. So the first vector is v1, and the second vector is v2. This gives us the change of basis matrix C, or C, B to E. So to form this matrix, we just put our eigenvectors as columns. So we'll have minus 5, 1, and minus 1, 1. What are the properties of our eigenvectors? So here the properties are that T of v1 is equal to minus v1. v1 is the lambda equals minus 1 eigenvector. And T of v2 is equal to 3 times v2. So v2 is a lambda equals 3 eigenvector. And then the matrix of T in basis B, we see that from here it's diagonal. So this is matrix D. And so the first diagonal entry will be minus 1. So this is the eigenvalue of v1. And the second entry will be the eigenvalue of v2, 3. So we'll get this diagonal matrix. And then we get our diagonalization formula, that A is equal to CD times C inverse, which is equivalent to this change of basis formula. Now let us verify this formula. So here we need to calculate the inverse of the matrix C. So for 2 by 2 invertible matrices, we have this formula. The inverse of the matrix ABCD is equal to 1 over determinant AD minus BC times the matrix D minus B minus C A. So here determinant of this matrix C is equal to minus 5 plus 1. So this is negative 4. So this tells us that the inverse of the matrix C, which is C e to B, is negative 1/4 times the matrix 1, 1, minus 1, minus 5. So the diagonalization formula predicts that A must be equal to the following product. So it is C, which is minus 5, minus 1, 1, 1, times the diagonal matrix minus 1, 0, 0, 3, times C inverse, which is minus 1/4, times the matrix 1, 1, minus 1, minus 5. So here, negative 1/4 can be put in front, and let's multiply these two matrices together. So here, when we take this dot product, we get 5. Then this dot product will give us minus 3. So then the next dot product is minus 1 and 3. And we need to multiply this by 1, 1, minus 1, minus 5. So this is negative 1/4 times the following matrix. So we have 5 plus 3, that's 8. Then we have 5 plus 15, that's 20. We have minus 1 minus 3, that's negative 4, and minus 1 minus 15, that's negative 16. And if we take this matrix and divide it by minus 4, then we exactly get matrix A. Let me point out one detail where we have to be careful. When we form the bases of eigenvectors, we can put them in any order. So any order will be fine. But then we have to be consistent, because the order of vectors in these bases will determine the order of columns in the change of bases matrix. And also it will determine the order of eigenvalues in the diagonal matrix. So the order of eigenvalues must match the order of eigenvectors in these bases. Let us ask ourselves the following question. Is every square matrix diagonalizable? So it turns out that the answer to this question is negative. Let us consider a couple of examples. So if we have example 1, so let's look at the following matrix. 0, 1, minus 1, 0. Now, so this will be representing an operator on two-dimensional real space. Now let us write down the characteristic polynomial. So here we have minus lambda minus 1, 1 minus lambda. And so this determinant is equal to lambda squared plus 1. And if we write down the characteristic equation, so lambda squared plus 1 is equal to 0, so then we see here that we have no roots. And since we have no roots, we have no real eigenvalues, and thus we have no eigenvectors in R2. And in fact, we can generalize this example, because this matrix is a rotation matrix by 90 degrees counterclockwise. And we can see that if we take a rotation operator of a plane by any angle which is different from 0 and from 180, then there will be no eigenvectors, because every vector is going to be rotated and it's never going to go to a multiple of itself. The second example, let's take the following matrix. So let's take the matrix A, which is 2, 1, 0, 2. So what is the characteristic polynomial in this case? So we take 2 minus lambda, 1, 0, 2 minus lambda. And because this is an upper triangular matrix, the determinant is equal to 2 minus lambda squared. So we see that we have an eigenvalue. So we have lambda equals 2 is the only eigenvalue here. Now let us look at eigenvectors. So if we take the matrix A minus 2i, then this matrix is 0, 1, 0, 0. And this is already in reduced row echelon form. So we see that this matrix has rank 1. So this means that its null space is also equal to 1. So the first equation says that x2 is equal to 0. So this tells us that the eigenvector with lambda equals 2 is the vector 1, 0. So what we see for this matrix is that we have a single eigenvalue, and there is a single eigenvector for this eigenvalue. There are no other eigenvectors that are not proportional to this one. So this tells us that for this matrix, we simply are not able to construct the basis of R2 that consists of the eigenvectors. And this was our requirement for diagonalization. And so the conclusion is that this matrix here is not diagonalizable. So what we see is that in both examples, we have a non-diagonalizable matrices, but they're non-diagonalizable for different reasons. So the first matrix is non-diagonalizable because our characteristic polynomial does not have real roots. And the second matrix is not diagonalizable because we don't have enough eigenvectors. So it turns out that the first abstraction of the first example can be overcome by going from real numbers to complex numbers. And this is something that we're going to discuss in upcoming lectures. So we're going to discuss diagonalization over complex numbers. But even going to complex numbers, we cannot fix all the problems. So this matrix will be non-diagonalizable no matter whether we are over real numbers or we are over complex numbers. Because so here, the characteristic polynomial factors even over real numbers, and we have a single root, but we have only one eigenvectors. And because we don't have enough eigenvectors, this matrix will not be diagonalizable. So we can formulate the following criterion for diagonalization. We can say that n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. Later, we're going to prove a theorem that says that this is also equivalent to the following statement, that the sum of dimensions of eigenspaces of A is equal to n. So in particular, in this example, we have one eigenspace of dimension 1. So the sum of dimension of eigenspaces is not equal to 2, the size of this matrix. And because of that, we don't have two linearly independent eigenvectors, and so this matrix is not diagonalizable. Motivated by the change of basis formula for linear operators, we give the following definition. Two n by n matrices A and B are called similar if there exists an invertible matrix C such that A is equal to C times B times C inverse. In particular, when we carry out diagonalization of a matrix, this matrix A will be similar to this diagonal matrix D. Conceptually, similar matrices represent the same operator, but expressed in different bases. We can generalize this formula not only for a pair of a standard and non-standard bases, but we can take two non-standard bases. So suppose we have two bases of the same space, B and S. So then we can write that Ts is equal to change of bases from B to S times Tb times the change of bases matrix from S to B, which is the inverse here. And so what we see is that Ts and Tb, so these are two matrices of the same operator but expressed in different bases. So this will be, so these are similar. This is how we should think about similar matrices. And because similar matrices represent the same operator, they will have similar properties. And so this is something that we're going to investigate next. Let us give several propositions describing properties of similar matrices. So we have proposition 1. If A and B are similar matrices, so this implies that determinant of A is equal to determinant of B. Now let's give a proof. So determinant of A, since A is equal to C times B times C inverse, is equal to determinant of C times B times C inverse. But we know that determinant of the product is the product of determinants. So we get determinant of C times determinant of B times determinant of C inverse. But we also know that the determinant of the inverse matrix is the inverse of the determinant. So this will be determinant of C times determinant of B times the inverse of determinant of C. Now this product is no longer a product of matrices, but this is a product of elements in the field. And whereas matrices did not commute, elements of a field do commute. And so what we get, this is equal to determinant of B times determinant of C by commutativity of multiplication in the field times determinant of C inverse. And so since the matrix C is invertible, its determinant is non-zero. So this inverse exists. And then we can see that this indeed simplifies to determinant of B. And we obtain that determinant of A is equal to determinant of B. So immediately we see that there are many non-similar matrices. So if two matrices have different determinants, then they are not similar. Next proposition is a generalization of this one. So similar matrices AB have equal characteristic polynomials. So let's give a proof. So what's the characteristic polynomial of a matrix A? It's determinant of A minus lambda times identity. But A is equal to C times B times C inverse. So we have determinant of C times B times C inverse minus lambda times identity. But now we can write the identity matrix as C times identity matrix times C inverse. Because indeed, if we take the product C times identity times C inverse, so this will still be identity matrix. So then we can write this matrix in the following form. We can write this as C times B minus lambda times identity times C inverse. And so now determinant of the product is the product of determinants. So we'll get determinant of C times determinant of B minus lambda I times determinant of C inverse. And just as in the previous calculation, we see that determinant of C will cancel with determinant of C inverse, and we get the characteristic polynomial of the matrix B. And we conclude that matrices A and B will have the same characteristic polynomial. As a corollary of this proposition, we get the next proposition 3, that similar matrices A and B have the same eigenvalues. And indeed, so this follows from the fact that eigenvalues are roots of characteristic polynomial. And since similar matrices have the same characteristic polynomial, their roots are also the same. So we conclude that similar matrices have the same eigenvalues. And this is not surprising, because we are thinking that similar matrices represent the same operator but in different bases. But if we have an operator, then its eigenvalues is something that's basis independent. So lambda is an eigenvalue of t if there exists a non-zero vector v such that t applied to v is equal to lambda times v. So this does not depend on the choice of a basis. And now we have proposition 4 that says that if A and B are similar, then trace of the matrix A, which is the sum of diagonal entries, is equal to the trace of the matrix B. So similar matrices have equal traces. We're going to prove this proposition in two different ways. So the first proof will be based on the following lemma. If X is an M by N matrix and Y is an N by M matrix, then trace of the product X times Y is equal to the trace of the product Y times X. Now let's give a proof of this. So the proof of this is purely computational. So let P be the matrix X times Y, and Q is the matrix Y times X. Then what is the entry Pij? So the entry Pij is going to be the sum k goes from 1 to n. It will be x ik times y kj. And then from here we conclude that the trace of x times y, which is the trace of the matrix P, is equal to the sum I goes from 1 to m P I, which is the sum I goes from 1 to m and the sum k goes from 1 to n. We have x ik times y ki. Now if we write the formula for qij, so this will be the sum s goes from 1 to m. We'll have y is times x sj. And then the trace of y times x, which is the trace of the matrix Q, will be the sum j goes from 1 to n q jj, which is the sum j goes from 1 to n and s goes from 1 to m. We will have y js times x sj. And what we see is that these two formulas are simply equal if we just set j to be equal to k and I to be equal to s. And so then these two sums will be the same. Now we can prove proposition 4 that similar matrices have equal traces. And so the first proof, so proof 1 of proposition 4. So the first proof is based on this property of the trace. The trace of xy is equal to trace of yx. So here, if we take trace of matrix A, so this is equal to trace. So since A is similar to B, so this is C times B times C inverse. And we know that the product of matrices is associative, so we can put the brackets in this way. And then, so we think that this is our matrix X, and this is our matrix Y. And we apply the formula that trace of xy is equal to trace of yx. So we get trace of C inverse times C times B. But now C inverse and C will give us identity matrix. So we get trace of identity times B, which is trace of B. And this gives us the proof that trace of A is equal to trace of B. And now let us give the second proof, which is also quite instructive. So here we can say that trace of A is minus 1 to the n minus 1 times the coefficient at lambda to the power n minus 1 of the characteristic polynomial of A. And we proved that similar matrices have equal characteristic polynomials. And if the characteristic polynomials are equal, then coefficients at lambda to the n minus 1 of characteristic polynomials of A and B will be equal. And because these coefficients are given by traces of these matrices, so we conclude that trace of A will be equal to trace of B, which we conclude by equating coefficients of the characteristic polynomials.